Welcome to Hacking Science.
The place where we take the densest, most influential source material and turn it into actionable, memorable knowledge.
And today we are strapping in for one of those papers that truly deserves the name Deep Dive.
We are tackling the fundamental shift that redefined modern AI. We're going deep on the revolutionary 2017 paper, Attention is All You Need.
Yeah, this one really changed everything. For years, the whole field, especially for tasks like machine translation, was completely anchored in these complex, recurrent, or convolutional neural networks.
Right, the LSTMs and GRUs, they were the state of the art.
Exactly. And this paper didn't just propose a small improvement. It basically proposed throwing out the entire established playbook.
It was a radical mission. They looked at the dominant architecture, the RNN,
Mm-hmm.
often with an attention mechanism sort of bolted on, and said, what if we get rid of the RNN part entirely?
And just keep the attention. Rely only on that mechanism.
And their claim was immediate and, frankly, massive.
Yeah.
They introduced the transformer model, and the results were just staggering.
The headline was, what, 28.4 BLEU on English to German translation. That beat the best existing models ensembles, even by over 2.0 BLEU points.
Which is a huge leap.
A huge leap. And doing it in a tiny fraction of the training time was, well, it was unprecedented.
Okay, so to really appreciate that leap, we have to start by understanding the cage they were trying to escape.
Mm.
What was the fundamental bottleneck of the old guard, the RNN?
The constraint is it's inherent in the design. It's purely sequential.
Like a factory assembly line.
That's a great analogy. To process a sentence, the computation is factored along the symbol positions. So to generate the current hidden state, what they call Theideller, you must first have the input for that step and the complete calculation of the previous hidden state, high to color.
So you can't jump ahead. If the input is a 500-word paragraph, you have 500 mandatory steps.
Mandatory steps that have to be done in order.
And that's not just a mathematical idea, it's a physical constraint on the hardware.
Precisely. That inherent sequential nature just... it precludes parallelization within a single training example. You can't speed things up by throwing more computers at one sentence because worker 5 always has to wait for worker 4's output.
So in technical terms, from the paper, what does that mean for training?
It means recurrent layers require sequential operations. That big O notation just means the time needed grows linearly with the length of the sequence.
So if your sentence doubles in length, the time it takes to process it also roughly doubles.
Exactly. And that actual and sequential constraint was the single biggest bottleneck holding back RNN training.
And it wasn't just about speed, there was also a quality problem, right? We've all heard of the vanishing gradient problem. How did the RNN structure make that worse?
It's all about path length. To learn long-range dependencies, connecting a verb to a subject that's 100 words away, the signal has to travel a long path. In an RNN, the maximum path length between any two positions is also dollars. That signal has to go through every single step in between. And with each step, it degrades. That's what leads to those vanishing gradients that make it so hard to form reliable long-distance connections.
So let me see if I can summarize the problem for you, the listener. RNNs are slow because they are strictly sequential operations in a row.
Mm-hmm.
And they have poor long-term memory because the signal has to travel too far in distance.
That's the essential insight. That's the problem the transformer was built to solve.
Which brings us to the revolution. The transformer gets rid of recurrence, relies only on self-attention, and the key change is this leap to heteroparallelism. How on earth did they do that?
Well, the core of self-attention is that it calculates the relationship between different words in a sentence all at the same time. It doesn't need that previous hidden state, 호르니나건.
So if you have a sentence with 100 words, it looks at all 100 words at once.
It computes the query, key, and value representations for all 100 words in one go.
Yes. So it's not an assembly line anymore. It's more like a parallel swarm of workers all calculating at the same time.
That's it. And the paper highlights this critical metric. The self-attention layer connects all positions with a constant number of sequentially executed operations. O-balls.
Constant. So it doesn't matter if the sentence is 10 words or 10,000.
The number of sequential steps is always 1. This allows for maximal parallelization on modern GPUs, and it's the main reason training times just plummeted.
And what about the path length? If every word can look at every other word simultaneously, that distance must just shrink dramatically.
It drops to the absolute minimum. The maximum path length between any two positions in a self-attention layer is also constant. It's $.
A direct connection.
A direct connection. The signal doesn't have to traverse 100 steps anymore. It happens in one. And that single detail makes learning long-range dependencies just exponentially easier.
Okay, I have to challenge this because it sounds a little too good to be true. If every word attends to every other word, the total computation has to scale up, right? Like quadratically. If sequence length doubles, the number of connections goes up by 4.
That is an excellent point, and it's a crucial trade-off. You are absolutely correct. The computational complexity per layer is $1 or $2 compared to RNNs.
So isn't that the new bottleneck for really long sequences?
It can be, but the crucial difference is that the dollar complexity is perfectly parallelizable. You can throw more hardware at it. The RNN sequential constraint of the RNN, you just can't.
So it's a trade. You're trading a slow sequential cost for a bigger but highly parallelizable cost.
Exactly. And for the kinds of tasks they were looking at, like translation, where knowledge is usually less than 1,000, the massive gain from parallelism just completely outweighs the quadratic complexity.
That distinction is the core insight. Okay, let's move to the engine itself, the transformer architecture. It's still built on an encoder-decoder structure, right?
It is. The overall setup is classic. You have an encoder that reads the input sentence and creates these continuous representations.
And a decoder that generates the output one token at a time.
Right, still autoregressively. Both stacks have 6 identical layers, but inside those layers there are no recurrent loops. It's all built from attention and some simple feed-forward networks.
Let's get into the mechanics. The paper really emphasizes multi-head attention. Why not just one big attention function? What does multi-head buy you?
Multi-head attention is the key to getting a rich representation. If you only had one attention function, it would essentially calculate one single kind of averaged out representation for every word.
Okay.
By using, say, 8 parallel attention layers, 8 heads, each head can learn to focus on different things, different aspects of the input.
Can you give us an analogy for what those different things might be?
Sure. Imagine one attention head learns to look only at syntax. It's just checking for subject-verb agreement no matter how far apart they are. A second head might focus strictly on proximity, like what word came immediately before this one. And a third might look for semantic relationships, connecting, say, king and queen.
I see. So it lets the model capture all these different kinds of relationships at the same time.
Exactly. Syntax, semantics, proximity, all at once. It gives you a much richer and more robust representation.
That makes a lot of sense. So how is this applied inside the encoder-decoder? The paper mentions 3 distinct uses. Can you walk us through those?
Right. They serve 3 different purposes. First, you have the encoder self-attention. In those layers, every position in the input sentence can look at every other position in the input sentence.
So that's where the encoder figures out what the sentence really means in context.
That's the one. Then you have the encoder-decoder attention. This is the bridge. Here, the query comes from the decoder, but the keys and values come from the final output of the encoder.
Ah, so this is how the decoder, while it's generating a German word, can look back at all the original English words.
And decide which ones are most relevant.
Exactly. This is the cross-attention we're familiar with, just, powered by this new architecture.
And the third type, the decoder masked self-attention.
So the decoder still has to generate the output one word at a time. We have to prevent it from cheating and looking ahead.
Right.
The masking does that. It ensures that when the decoder is predicting, say, the third word, it can only attend to the first and second words it already generated. It masks out any information from the future.
Got it. Preserves the autoregressive property. And all of these use what the paper calls scaled dot product attention. We have to talk about that scaling factor, the $1 score to you. Why is that little detail so important?
It's all about numerical stability, specifically preventing the softmax function from saturating.
What does that mean in simple terms?
If the dimension of your key vectors dkk is large, the dot products between the query and key can become huge. And if you feed really large numbers into a softmax, the gradients become tiny, almost 0. So it's like you have 1,000 options, but the scores are so extreme that one option gets 99.9999% and everything else gets nothing. The model stops learning the small differences.
That's a perfect way to put it. It can't learn the subtleties. The scaling factor just keeps the dot products in a reasonable range, ensuring the softmax has healthy gradients so the model can learn efficiently.
Okay, so we've established the transformer ripped out the sequential part,
Oh.
but with no recurrence, no convolution. How does the model know if a word is at the beginning or the end of a sentence? How does it know about order?
It doesn't initially. That's why you need positional encoding.
Right.
Because attention is, by its nature, position agnostic. It just sees relationships. To give it a sense of order, the authors created a set of fixed sinusoidal functions, like sine and cosine waves of different frequencies, and just added them directly to the input embeddings.
It's like giving every word a unique mathematical fingerprint, a kind of built-in map of where it is in the sequence before the self-attention even starts.
That's a great way to visualize it. It allows the model to learn about relative positions, how far apart two words are, as well as their absolute position. It's a very clever way to inject order without a sequential process.
Let's pivot to the payoff. For you, the learner, this is where the architectural genius turns into real-world results. How dramatic was that speed advantage?
It was revolutionary. The base transformer model trained in just 12 hours on 8 P100 GPUs. The big model took 3.5 days.
And that was fast for the time.
The paper explicitly calls it a small fraction of the training costs for the best models that came before it. Those often took weeks.
And the quality metrics prove that this speed wasn't a trade-off.
Not at all. The parallel architecture delivered a decisive quality leap. On the benchmark English to German task, the big model hit 28.4 BLEU. That was a new state-of-the-art.
And on English to French.
Even higher, 41.0 BLEU. It just confirmed that this Orgel-Huntsent path length structure made these complex tasks both faster to train and empirically better.
Before we wrap up, there was also a nice side benefit the authors mentioned, right? About interpretability.
Yes, that was a really neat finding. Because it's all based on attention, you can visualize what the model is looking at. They found that different attention heads were clearly specializing in different linguistic tasks.
Like what?
Like one head might focus just on verb phrases, and another might be resolving pronouns to their nouns. It gave this new level of insight into what the model was actually thinking.
Okay, let's bring this all back for you, the learner. What is the fundamental principle here? What defines the transformer's success?
It's the shift from sequential, time-intensive computation to maximal parallel computation. It's that simple. By replacing the constraints of RNNs with self-attention's Euler constant path length, they simultaneously unlocked massive GPU parallelism for speed.
And made it fundamentally easier for the model to learn long-range dependencies, which improved quality.
That's the whole story.
That structural change has defined so much of AI research since. And the authors were incredibly forward-looking. They said they were excited about the future of attention-based models beyond text. So here's a provocative thought for you to explore. The transformer's big weakness is that quadratic computational cost, that Newton complexity for very long sequences. So how is current research trying to fix that? How can you get that cost closer to linear to one color while still keeping the revolutionary path length to make it work for truly massive inputs like high-res video or hours of audio?
That's the big question right now. A great challenge to consider. Thank you for joining us for the deep dive.
We'll see you next time.